This conference will now be recorded.
I thought you were muting me. So Steve Mould basically does everything to the nth degree. It really sort of nice, good way for students, both GCSE and A level. And what Steve Mould did, he started his sort of video on this with a balloon full of helium. He talks behind it and he goes quieter because, of course, you're refracting the other way. So, when you're teaching convex and concave lenses, his video is fantastic. And again, I will make sure that gets out to you. I'll put it in the link when I get a minute, because it's so worth watching. And he takes everything to the nth degree. Look, he even took the balloon apart, put a copper ring in just so it had a better shape, so you could get a better effect from it. So it's amazing what you can do with carbon dioxide and balloons. Again, this fascinated me when I saw this picture. I bought a couple of books, really old books, just to get these pictures. And this is what's really interesting here is there's a balloon here. I think it's full of sulfur dioxide or something, but it's a dense gas, yeah, sulfur dioxide. And this is shielding a spark, and this is that Sherlin sort of photography where you can photograph shock waves. And the shock waves moving out from the spark heats the air, a shock wave moves out. You can get a single wavefront, which is why this sort of photography is really good for this kind of thing. And look at how the sound has refracted. And what I really like about this is that, one of the directions I've taken this talk before is to talk about sort of auditoriums, and it's one of the things that Trevor, if you were at Trevor's keynote the other morning, he's one of the things he works on is how to build auditoriums and the considerations. And here you can see the one below is interesting. I'll show you a picture in a minute. Why I like this is it's a ripple tank. It's basically a model ripple tank. And nowadays, to be fair, most of this stuff's modeled on computer modeling, because you can model how the waves bounce around structures very effectively. The maths is known, it's only some kind of differential equation. But what was interesting in the olden days here is the way to actually look at how your auditorium would function acoustically. Try saying that at this time of night after 2 days. What it would look like. And here, this is the where there's a spark again, and why you can really see the difference with this spark and the Sherlin photography. You can really see just one wavefront, so you can see how, and it's very important. And there's so much, we won't go too much into it. We're going to touch on it later, but so much goes on in designing these buildings to get the acoustics right. In fact, Trevor, who spoke, that he's got 2 books, and Sonic Wonderland, again, I'll probably show you that at the end. It talks about all sorts of things to do with this kind of phenomenon. But what's really interesting, there was a building where the architect, unbeknown to the architect, had built some weird sort of curvy ceiling, and it was in an auditorium in a train station or something. And when people walked towards the ticket office talking, it put weird echoes and reverbs in there, and it really sounded different. And they were suing the company was suing the architect for having this weird sounding warble in their building, which wasn't in the stipulation. However, people got wise to it. They started coming to see it, and bands came and recorded in this space. And later, a plaque was put up about the wonderful architect that designed this this structure as an acoustic sculpture. So the shapes of buildings are important. And here you have, this is just this national physics. What's interesting, actually, we're going to talk about the National Physics Laboratory later. They just were people that gave you a very good toilet roll way of working out the speed of sound. So they've been around for a very long time. And this is how they used to check out buildings. So the picture you saw, this is the actual ripple tank that was being used. Fantastic. What's Helen saying? Let's have a look. I get you, the old ripple tank. That's right. And you could project it up onto the ceiling, couldn't you? So that's right, yeah. Now, again, how do we visualize sound? So there's plenty of resources, and we've spoke about resources already in the last few days from the IOP on IOP Spark. Generally, most of the old stuff's been migrated on there, so you can find things. And I shall put links to this kind of thing on, but let's just talk about visualizing sound for a moment. So this activity, this activity again is just about watching these things jump. You're going to tap a tin and watch the little beads or the sprinkles jump up and down on the sound event. And this is great. This is great for even primary students if you're doing some sort of primary liaison. And this is, sorry, let me just go back. This is in, not only is it on the Dancing Springles, but one of the reasons why it's worth getting classroom physics, why it's worth being in the school affiliation scheme, although you can get access to all the classroom physics via having a registration for Talk Physics. And actually at the moment, they're out on Spark anyway. They got released to help people. So they used to be, you had to log in to get them. Now they're out there, all the old classroom physics, and there's so many things in there. This is the March 2020 a pull out on sound, which had this activity. Now we know when we get onto A level and even at GCSE, you want to show students standing waves. Now this is now it's the one link I've not given to Graham, but we will find this link before. In fact, I'm going to show you this because you need to understand how amazing this is. So if I go to YouTube, this won't take a second, and I go to oh, I don't think my computer's been off for a few days. Now, what Charles Taylor said about Chladni, he was a rare physicist in that he went into physics for the fame. So again, we're not going to watch this video. Let me just find something that's referenced at the bottom of this. Here we go. This is what we want. Now, this is incredible because there's a book as well that I'll tell you about was written about this Christmas lecture series. And again, what I'll do is I'll just pop that into the chat.
Not related in the same way that the notes were on string. They're very complicated relationships which we don't need to go into.
Right, let's get rid of that. And then just show you this momentarily. Now, it's on number 3. They're all there. You get it. But it's a Christmas lecture. There's 5 of them. I can't remember the year now, 1989. And for years, I used to email the Royal Institution saying, please put this up. I know you've got a video of it. Come on. And now it is. And there's 5 of them. They're fantastic. So the links for number 3 there. Make sure you copy that. If you do nothing else, make sure you copy that and watch those. Maybe not in a row, but they are fantastic. I'll tell you something more about those in a minute. Now, let's go back to the PowerPoint. Sorry, guys, wait a minute. Right, here we go. Now, what's interesting, again, I'm not going to show you this, my one at college. What I learned very quickly to put white sand on and not salt, because everything corroded with salt. And you know the sort of thing. This is just a piece of plastic cut. You can get all sorts of fancy ones from Timstar in the shapes of violins. This is just a piece of plastic we cut, connected to the vibration generator. But over here on the left, our mate Charles, look at how he does it. It's incredible, because I've always known you can bow them. But if you think about it, the one on the right, what I do is I've got a SIG-gen into that. Okay, I've got a SIG-gen into that, and I'm sweeping up through frequencies, and I'm getting a change in standing wave pattern. Basically, the thing vibrates, a wave comes to the edge. Remember the things that are important to students, that a wave reflects and superposes and interferes with itself, and that's happening at the edges. And these modes are really important. You make really pretty patterns. But look at Charles, he's forcing the notes with his fingers and then bowing. And when you watch those videos, you won't believe in this. They're amazing. They really are amazing. He will, you'll see him do this with various patterns, force various patterns. Obviously, he knows where the nodes are, puts his fingers in the correct places, and you get to see that. Now, again, Graham, if you could pop in the next video, which is the, what have I called it in my...
Chladni balloon.
Chladni balloon, that's the one. Of course it's a Chladni balloon. How are we doing, guys? I know it's late and you've been going for days. No one fallen asleep yet? Now, so again, you watch that. A couple of people tell me when you're done, and then we'll start up again.
I was having issues with my microphone before, David, but a couple of people were asking, is there a difference between auditory density and density? So you mentioned at the beginning, you talked about acoustic density and density. Is there a difference?
I guess the thing we're really talking about is acoustic density. That's right, and whether that's different, I think it's mainly based on the density of air. It's probably based on humidity and a few things as well, a few other things. It's all going to be to just do with the speed at which, or the rate, I guess, at which they oscillate backwards and forwards. It's a good question. I'm going to write that down as well, because there's something in the Charles Taylor book that says something about the carry. It's really interesting what the word analogous means. Oh, this is what my students do to me.
I'm sorry.
Analogous is an amazing word to understand what analogous means, because you have sound waves hit a speaker, and those sound waves move that membrane in and out. And actually, I keep meaning to develop a resource from the knowledge my son has and the other people I speak to at Salford, based on, because it's all Hooke's law, Faraday's law, and there's something else I can't quite remember now, but it's just all A-level physics. And basically, as the pressure wave changes and pushes the speaker in and out, then that obviously moves a magnet that induces an EMF. This is where the word analogous comes from. It's that the electrons, or the imposed shuffling backwards and forwards, we know they're all moving around randomly as well, but that imposed shuffling backwards and forwards is meant to carry the same characteristics as the air shuffling backwards and forwards.
Yeah.
And this is why I think there's more to acoustic density than just density, because Taylor goes on about the characteristics being conveyed. He doesn't really say too much, and he's talking about characteristics beyond frequency and amplitude.
Well,
things probably like phase and stuff, but hey, come on now. This is meant to be a live talk.
Sorry, I was distracted here. People are talking about singing bowls and things like that, but let's get on.
So let's talk about the balloon over the glass, Kevin. Okay, so the thing about that is, I just want to say one thing. I would do it differently now in terms of your own safety. The principle's the same. I'd use a straight-edged, thick circular glass, if that makes sense. Wine glasses, I remember when I did this, it was very fragile. They're very fragile, aren't they? And you wouldn't want to, because you have to put quite a bit of force to stretch the balloon over. I'm using the light, cheap balloons from those Poundland Queens. But you basically stretch that rubber over any glass, but pick a thick glass. And then what you can do is what's driving that. This is what I liked about this. Is why I want to show you this one, because you know what's going on with vibration generators. But if you've not got one of those, this is I can't think what they call it, an iPad on the left. I can't think what they call it. An iPad on the left. You can see in the top left-hand corner, that's an iPad. And there's no, that's just being played at normal full volume. And then that drives that, and I'm as you saw, sweep up through the frequencies, and you see the different standing waves when it changes from one to another. What's Daniela saying here? Okay, now, so let's think about visualizing sound. So the next thing I wanted to talk to you about, so Graham, this is UV standing wave. So again, if you want to have Graham pops that in the chat, and I'll have a quick look and see what people are saying. Yeah, so Kevin was asking, is the speaker alongside? So that's the iPad. Sorry, guys, you're watching that video, aren't you?
It's a very short UV standing waves on.
It really is, yeah. So just tell me when you're done.
Yep.
I tried to pick nice short ones. Now, the important thing about this is, and again, a word of caution here, if you were to set this up. This is my shed. I do have UV glasses, and I've got a tube, and obviously you're just looking at visible light from the screen. If you were to replicate this in the classroom, all you would need is something in front of your UV source that blocks the direct line of sight, and then I think it would be okay. Otherwise, UV can be a danger if you're too close to it. My daughter worked at Blackpool Pleasure Beach and she was painting all the Alice in Wonderland ride, and she rang me in the afternoon once saying my eyes hurt. I said, what are you doing? She says, I'm painting in the UV hall. And I said, you know, have you, got what sort of glasses on? She says, well, I can't, they haven't given me any, and I can't wear glasses because I can't see how it fluoresces. I need to see what it looks like. But, you know, it's not a good thing. So you've got to be careful.
Not a good thing, no.
Now,
Which is why Phil's saying, why use UV? Or Dominic's saying, how does it actually work?
Now,
so
the thing about I'm just doing the UV to highlight it.
Okay.
Just to make it, just to highlight the motion. It was more, Phil, because I could. And it does, I mean, there's no benefit to it. And actually, if you watch the, so it was just really to, just to make the node a bit brighter, you know, it's just enhances the sort of look of it, really. But let me tell you something about the Charles Taylor. You can tell I really like that Charles Taylor videos. He does this, right? Get this. I hope I can explain this effectively. He has a wire that he passes a current through. It's a resistance wire, so it glows red. Now, where it's at the antinodes are moving, it cools enough to not glow red. But at the nodes, it gets hot enough to glow red, if that makes sense.
Oh, I like that.
Yeah, and it's fantastic. I mean, a hot wire with a large current going through it is a lot more dangerous than my UV setup. Come on now. But isn't that amazing? Isn't that amazing the way that's set up? You're going to love that. Honestly, I did put the link in today. You're going to love those videos. Yeah. So, sorry, I'm laughing at Phil. I've known Phil for a very long time. So. Oh, no, we don't want to do that. Do we? We want to go to the next. And again, we don't need to go into all these relationships. You understand these relationships. You teach these relationships. You know, you're showing these kind of relationships. But what's interesting is, I don't know about the other exam boards, but AQA A level only deals with waves on strings. It doesn't deal with, and it's sad really. I still show students because there's so much here that's fascinating about this. And you know, the setup we use, you can alter the height of the water in the tube and show when the column's resonant. You can work out the length, and with the frequency of the tuning fork known, you can work out the speed of sound. And this is something that David Farley done very well in our Prelude to the Physics of Music. Again, we can put a link to that, and you can go and check out some of the things there about sound, very similar things. And one of the other ways, again, in fact, I want to just do one. There was one more video to watch, Graham. Sorry, it's my fault. It was the resonance in a pipe.
It's your standing wave tuning fork, wasn't it? I think it's...
Yeah, that's a good idea, Helen. You don't need what you're about to see. Actually, the video is using a similar thing to what you're saying, really. But the water, it doesn't need to be that big. It doesn't need that amount of water. That's just, I just used that because it was around. So again, just tell me when you. Yeah, Phil, the transformer melting nails. I thought we're doing sound. Yeah, we've had that kit in college. We had that. I knew he'd be here. Right. Okay. So again, just an example of showing you standing waves in pipes, finding that resonance. Always good for teaching resonance as well. But I wanted to remind you of this for a specific reason. And just before I do that, again, we don't need to. I suppose I can just try playing it, can't I? Because it's the visual you need. But what's interesting here is that for a long time now, these, again, another good way, one of the things we're very passionate about at the IOP is doing things cheap for you, so you can see how cheap equipment. There's no point in coming to some workshop and seeing some £750 vibration generator, or I don't know how much they cost. I mean, the ones in schools often cost about £70–80. But this is electric toothbrush. Now, why I want to show you this is Darren is doing this so well. I used to do it on the horizontal, and it's really hard to keep the tension in the string right. So the nodes are all over the place. And then I was shown this way. And again, what you can see is that the tension stays equal with the weight, and the nodes are fantastic. You can see everything. So this is the cheap way to do standing waves on a string with an electric toothbrush. I'm sure you've all seen that before, but for me, you know, I held it horizontal for so long, and then as always, people modify and show you good things, don't they? Now, So that's standing waves. So let's think about how sound is made. And this is a new one, actually, a new avenue I've taken this talk down. And again, it was due to reading, well, I shouldn't say this, it was due to my son reading Trevor Cox's book and me having discussions with him about it, because I've been reading all these other books. But what is interesting, I think I said this at the introduction to Trevor, is that every time I've gone to talk to my son about something in an acoustic book I'm reading, he goes, "Oh, Trevor mentioned that a few pages back," but you know. And what we're looking at here is how you make a sound. So, the system starts by you have to get a vibration, you need a vibration. And basically your vocal folds, and I won't show you any. If those of you that were there the other morning, some people should have a warning about vocal folds, shouldn't they? Some people don't like that corporeal image. But basically a mayonnaise, what took me in this direction was I was looking at a mayonnaise lid longingly. And I realized that when you press it, it comes out and then snaps back, comes out and snaps back. And that's what our vocal folds do. And we'll talk a little bit more about why that's important, that it's a saw wave in a minute. So with the vocal folds, the Poundland Queens need a rest. Come on now. Now, the thing about this lid was, I will just tell you this, I'm not going to show you the video because I didn't make one. I did find someone with a little video in slow-mo, and they let me use it. But we won't look at that now, but it basically pops out, snaps back, pops out, snaps back. Now, often people sort of show balloons as what happens to the vocal cords and what's happening, and there's a sense in which it has to be pop out, snap back, but there's nothing wrong with this in teaching people that you need vibration to make sound. So there's nothing wrong with balloons. And what's really clever, I didn't realize this until researching this a bit the other day, is that when you speak, your brain calculates the length of the sentence you're about to say and regulates your breath to come, because that's something we can do that apes can't. Again, we've developed all these ways. We can regulate the way, on top of breathing, we can regulate the way our sound comes in and out. Other animals tend to have to communicate or make the sounds as part of their breathing cycle or part of their breath. We've evolved away from that. And in some ways that's been at a cost to us, because the way our esophagus is protected and the position of the vocal cords has moved to a dangerous position in terms of choking hazards compared to other animals that evolved not to choke on their food. But it's the playoff, like all of these things, jaw dropping. That's the playoff, the evolutionary playoff, and that's meant that we can communicate. So yeah, what was I going to say next? So I've shown you that, so I don't want to show you that. Go on. That's what I want to do. So again, just going back to standing wave and tube. So this is I just did a screen grab from a David Farley moment we had on speed of sound. And again, you can go and look at this elsewhere. It's well done. In fact, there's a very good book called Using Physics, Gadgets and Gizmos. I won't waste time putting on the screen now. I should have done really to show you. I'll put the link. I'll make sure just at the end I'll fire some links off, because this book really goes into this. And the main reason I want to show you this is just get aware of boom whackers. Boom whackers, the music department will have them. You hit them, that obviously sets a vibration in here. And again, we won't go into all the physics of this. There's other things to talk about right now, but get interested in boom whackers. And then another way of doing it, David did, again, speed of sound with tubes, changing tube length, different frequencies. C is F lambda, so you're going to work out your length. Remember, it's not the length of the tube, you've got to work out the standing wave, the wavelength, like from the previous slide here for an open. And as we're saying here, that boom whackers, you can buy a cap. I don't think they come with this, a cap that goes on the end that then changes it to a closed pipe at one end, and you get a different frequency. One's a double of the other. I can't remember which way around now. But why this in this talk? You know, again, as I say, we're not. Let me just say as well with that. That's the thing that was also recently. There's very good things with the toilet rolls with the National Physics Laboratory. Again, we'll make sure these links get to you if you've not already seen that. But that is out there as a way you can work out the speed of sound from standing waves with a toilet roll. and playing frequencies in. The other way that's quite nice is there's a program, we're going to talk about this if we get time, called Audacity. And with Audacity and a pair of stereo headphones, you can spread the headphones apart, and Audacity will pick up on the transit time, so you can work out the speed of sound. That's sort of an older way of doing it. Now, why, though, in this talk, why in our talk here, what we're interested in is the vocal tract. So we've got our oscillator, we've got our oscillator down here. It's making a sound like we would play into an open, I think it's a closed really, open at one end. The problem with what I'm about to say is it's much more complicated, but the gist of it is this, and this is an interesting book as well. I should really make references to the book so you can order them. But this is, in fact, I'll find the title later, but it's worth buying. These books, this book is, going to be £3 or £4 on Amazon, somewhere like that. Now, what's important here is that you can see that when we make this vibration, we get resonant frequencies from that in our vocal tract, and they're called formants. And we control, when we speak, which formant is dominant, which frequency. And actual opera singers have techniques. If you Trevor's talk, they have techniques for pushing up into these higher formant ranges where the frequencies are more resonant with our hearing, so they can be heard above the orchestra. And remember, he also, what was interesting about his talk as well, he said that they have to, the warbling, the variation they do is because our brains pick out variation over other music, over the music. So we listen, we notice that oscillatory motion sort of thing. But the important thing about this is these are standing waves in your vocal tract, and they basically they're called formants, and we change the shape of our mouth and all sorts of things that sort of it's too numerous, and I'd have to think as well to remember. But let's just say you change the shape here. You can see what's going on in some of these. You lower the palate, you push out this way. You don't even realize you're doing this. But what's interesting, so hopefully you can see the can you see the oscilloscope, Graham? Now you can actually, I can tell because
yes, you can do. Yeah.
So again, remember this. I've harped on about this a lot, but I know if you follow me on or see my posts on Twitter, you'll know that I didn't stop going on about it for a couple of weeks. But it's just so incredible. I've been waiting all my life for an oscilloscope like this, And Firefox as well. It's very good. Firefox is is the next level from this. And if you go and download this, you get the sound card oscilloscope, which is the thing I'm about to show you. You get a student instruction sheet, and there's a really good video by Nilafar to show you students. It's for students to sort of get instruction. So here's the oscilloscope. I'll just show you a few things about this oscilloscope because the basic thing is that you speak into it. If you're not careful, you'll get two lines here because it's basically it's dual channel. So if we're just talking into the microphone, playing instruments into the microphone, just basically make it a single channel. The other thing is this thing called trigger. It's best just to go to normal for trigger. It's, I mean, my son's, like I say, got a degree in acoustical engineering, and we were talking about it for hours, what it really means. So I just go for normal. Let's be normal. And then what you can see with this is you can do all sorts of things. So when we look at those vowel sounds, like A, E, you can see they are regular patterns. I'm gonna have to have a drink. They are these regular patterns. They are these standing waves. But what's really interesting about this, sorry about that. What's really interesting about this is this thing has a frequency analyzer, okay? Now the frequency analyzer, when I click on this, and again, the best thing is to be on log. I really need to make a crib sheet for this. There's not much explanation with it, but it's brilliant because it's free, and it's the person down here, someone else can pronounce that later, they basically gave this to the Institute of Physics for free use for teachers and students. It is a substantial piece of oscilloscope, really. So go to log. Now I can't do owl sounds, but what I can do is do a vowel again, like A, E, A. Now if I freeze the screen, that's the other thing. You can freeze the screen. It's really good. You can freeze the screen. And the other thing, what you can see here is that this is that fundamental of my vocal tract. This is the fundamental resonant frequency of my vocal tract. And these are the higher harmonics. And I mean, if you were inclined, you could even start to go and look at the mathematical relationships from the numbers here. We'll leave that one for Phil. Phil said he's free later. But you could work out all the, you know, the relationships and prove that it's standing waves. So it's fantastic. Now we're going to come back to oscilloscopes. I just wanted to show this bit here. So we'll close that down. Let's go back to my PowerPoint. So again, this is just showing really that, what I should say, I should have put these the other way around. What really, a long time ago, I remember going to an institute of physics, because what a lot of us, you know, as coaches and things do is, what the institute's very good at doing as well is not only providing these events for you, bidding for these things that I mentioned surveys yet, but what's really important is they get us to actually get together. And Graham will confirm this, and Phil and that, and we, you know, we have these days where we all meet up and plan things and you know, this kind of thing. And I remember going to something years ago, and there was this thing on the voice box in physics. And to be honest with you, sound wasn't my thing back then. I mean, obviously I was polite and listened and everything, and did the activity. But I remember later, a few years later, thinking that's what that thing was all about. And it's amazing. It's all about the evolution of the voice box. And again, I will put the a link to this. The problem with this at the moment is, well, not a problem. It's on the STEM Learning website, so you need to log in to get it. But if you know, again, Talk Physics STEM Learning, if you haven't got logins for those yet, that's your homework for this conference. And it's you know, it's really, the whole program's there, the whole booklet, you can access it. There's other universities that have done similar things as well. So there's a lot out there about the evolution of voice. And this really tells the story and shows you how to make these little resonate. What you can sort of see in the bottom left-hand corner is it shows you how to make resonators that make vowel sounds, particular vowel sounds, because of the resonant frequencies that they support or promote, if that's the right word. But you know, well, it's worth looking into this. Now then, the other thing. Bear with me one moment. Now then, the other thing is that. I've got some really heavy books on acoustics. This isn't the heaviest one, to be fair, but it is heavy going. And Hermann Helmholtz was one of the first people really to really explore sound. You know, he was really exploring it. And what happened is that these are like what we call Helmholtz resonators, but they're bottles to you and I, and you blow across the top, the air moves up and down, and these oscillate again at very given frequency, and you will get some resonant frequencies in there. But the main thing, in fact, I've not decided to go down that route today, it's a shame, but if we were to look more at Helmholtz resonators, what's really interesting here is Helmholtz sat in front of the orchestra. Remember, none of this fancy frequency, none of this, oh look what frequencies are present in that instrument. And if you were at Phil's talk yesterday, then oh, you poor things. No, sorry, if you were at Phil's talk yesterday, then you will have seen how the timbre of an instrument is to do with what frequencies are present. And what people like Helmholtz did was they sat in front of the orchestra, basically with different sized bottles, and they knew the maths. Now it's slightly more complicated than that. It had a hole in it that it had basically a bit of glass he could stick in his ear, like a hole into the thing. But really, what he was doing is in the same way that if you were to take on a very windy day this set of bottles, and you know, some of them would have a resonance from the wind blowing across them, he was literally just saying, well, this is my resonator that resonates at 440 hertz. You'd sit in front of an instrument, and if that one was louder than other ones, it was at resonance, and therefore he knew that that was a dominant frequency in that instrument's timbre. So in fact, you can thank him for that. But there is a heavier book, and it's Lord Riley's book on, I was laughing at my son about how much maths was in it, and it's a very old book, but it's an appraisal of Helmholtz's book. So they're very interesting. They're all cheap on, in your booksellers, secondhand, and they're worth looking at. So another thing, again, it's late on a Saturday. Normally I'd be getting my camera on, showing you these things, but we can just discuss them. And the important point is you replicate them in your classroom, not necessarily see it done by me. But this is another way of showing sound. Now, one of the things I forgot to mention at the very beginning that was interesting about that oscillator, I've not looked at the chat for ages. Of anything coming up? You guys happy? Now,
I'm keeping up with you, Dave. So I think so. Yeah.
That's good. That's good. So one of the things the thing that drove the electronics industry is another really important thing. And Graham, when he's seen this talk before, knows that sometimes I go down the route of making basically a tuning fork into and making a guitar pickup. But I've not gone down that route this time. But again, I'll write it up because you can make a guitar pickup. But what's really important is that the important thing about that is what drove the electronics industry was amplification and the ability to make a continuous wave, a continuous sine wave or trigonometrical wave. The continuous wave was a carrier signal, so you can use heterodyne mixing to send weak signals. So my dad was a radio officer in the Merchant Navy, and I talked to him quite a lot about these methods and techniques. One of the things was that you had to detune to extract out from the carrier wave your signal, and there's some amazing physics there. In fact, the ear, we haven't got time to go into this either tonight, but the ear is incredible. Where that avenues of exploring that took me was all about this thing called heterodyne mixing and how you need an asymmetrical oscillator that responds to the incoming. It's fascinating. It's some really good stuff there for students for EPQs, actually. We won't go into that now. The important thing, though, is that I needed to generate a continuous sine wave, but in this case, what we're interested in is I also needed amplification. And the search to find an amplifier was crucial to the development of transistors and electronics in general. Now, this isn't true amplification, but what's quite, I just remembered something, I must tell you this. So I sent my son's friend said to me, come on, Dave, I'm furlonged and, I'm bored and I like sound. They're musicians, play instruments. He says, come on, teach me a bit about sound. So I sent him a tuning fork in the post. And I thought we could start discussing sound with the tuning fork. So he's tapped it and put it by his ear. And he's messaged me back saying, Dave, that was really quiet. It's much quieter than I thought. And I said, well, yes, that's because, your forks are pushing away a very small amount of air here. So that it is quiet. They're just quiet because for that reason. I says, but if you tap the tuning fork and get a paper cup and put it on the paper cup, and again, I'm not going to waste time doing the demo today. Yes, that's right. And put it on a record. In fact, that's right. We said this was informal and interactive. Let me just see then if I can do this. Let me show you something. So basically what this poor lad did is he took me at my word. I meant just put the tuning fork on the thing and hear it get louder, but he put the cup over his ear and tapped it with the tuning fork. So I've ruined his career as a musician. Now, what I want to show you is this. Now, the other problem I have is I never call anything on my YouTube channel by the right name. And I can't spell Bolero anyway. It's quite a recent one though. But what I wanted to show you is just how I play a tune with a record with a £5 note because it has the stiffness. Again, just what I'm going through here, this is my YouTube channel. Like I said, they're all really for things that I've put on Talk Physics. So as explanations, I put them here and then embed them on Talk Physics. So you're welcome to look through this. If there's anything you want, I could probably point you to where we spoke about it on Talk Physics. And if I can't, then you can ask me questions about it. I'm not going to waste time looking at it. But what I was responding to there was Andrea saying about making an amplifier, that's right, and making the sound with a pin. Oh, have you found it, Graham?
It's not yours, it's somebody else doing it.
Okay.
Sorry, I haven't been able to find yours
No, that's
yet.
okay.
Yeah.
And you did the hits. Just tell me when you're done. But that, yeah, and that's right. And in fact, in the office of there was a very good video with someone doing it with a cup and a pin. With a cup and a pin. I don't know which video you guys are looking at. Actually, I'm getting into a bit of a mess with tabs here, but yeah. And in fact, I remember when we were young, me and 4 people, we were teenagers, and we were sitting around some flat somewhere wanting to listen to music, and we put the headphones of one of us had a Sony Walkman. I mean, things like that weren't big, you know, then. One of us had a Sony Walkman, and they put the headphones in a pudding bowl, and we all sat around listening to the music. So now remember that also, though, that's in a way that's not amplification. You're concentrating the sound, and we'll come back to that in a minute, what we mean by that. Now let me just go back to my PowerPoint. Okay. And the slow-mo guys have a really good way of doing this with the tuning fork. In the olden days, nowadays you can connect tuning forks to microphones and oscilloscopes, and you can. Do you know what? I've still not tapped the tuning fork and played it into the. Oh no, I have. I've done it. It's okay. I think I've got a picture of it. Listen, come on, Dave. Stop. Let's stay on piste. Now, so again, the slow-mo guys very good at showing this, but the old way of showing that a tuning fork had a trigonometrical sort of sine type graph was they used to attach a pin to it and pull a smokened piece of glass underneath it. So there are, you know, nowadays we're lucky, and like I say here, we won't look at it now, but those slow-mo guys, they do an amazing thing with a tuning fork. So again, visualizing sound, and again, one of the things I really like looking at is the old ways of doing things. This is a book by Millikan, actually, of oil drop fame. A very good book. I keep meaning to. I could never do a shelfie. I've really got too many books. It would take too long. But I keep meaning to sort of grab a few each week off, take pictures of them, and just put them on Twitter, just so, because the books I've spent years just realizing, oh, there's that book, finding it in a secondhand bookseller. Most of them cost £3 to £5, you know. So I must do that. But anyway, this is Millikan's book, and what you've got here is inside here, the tuning fork oscillates. It basically sends the air, you know, the air in this tube backwards and forwards, oscillates this diaphragm, and therefore the gas that's being entered to go into the flame gets oscillated, and the flame dances. And this, you know, remember pre-oscilloscopes, it's amazing the ingenuity they used to use. And you can actually look at the response. You can do this. You can look at the response to a flame for ultrasound. One of the ways of visualizing ultrasound is with a flame. So you can drop high tensile pins and watch a flame respond to the ultrasound. Again, bat sensors, bat detectors. I'm not going to go into those either today, but one of the things I really got into with this talk was a bat detector. And you can listen to, you know, jangling keys, all sorts of things, not just bats. There's loads of things that produce ultrasound. And this just, you could find from the periodicity of the flame flickering. This is just a mirror that you rotate just to get a stroboscopic effect, so I can still the flame. And this is the way I could measure the frequency. Of course, nowadays, what do? We do these. I do, Jenny. I have so many physics books. I do. It's terrible. I don't know where to put them all. I've run out of cupboards at college as well. Now, so this is an oscilloscope. Obviously, it's an oscilloscope. You know what oscilloscopes are, and we've been looking at the thing. But this, it used to always not annoy me, but so we got the oscilloscopes out. We're very lucky in my college. We have a class set of oscilloscopes. They're very old, but we managed to maintain them, and they're okay. And we always just used to get the 50 hertz, you know, the power pack out, and they'd look at 50 hertz on them. And we do have a SIGGEN that you could look at it with, but it's so easy nowadays. Like you can see here, to just connect, you know, an MP3 player or something into these things. The cables are easy to get. There was a time you had to sort of make the cables yourselves, but they're easy to buy now. Rapid, CPC, they just sell the cables. And you can do amazing things with the oscilloscopes. So what I wanted to first show you here, in fact, I want to say one more thing because I've only just come across this recently, so I haven't got a slide on it. But this is amazing. So computer games, again, this is a really good hook for students. Students will like this. So computer games, they all like playing computer games. What came first, the graphic, the graphics card or the computer game? How was the graphics done? So they had these little chips that people could put games like, is it Pong, the tennis game, isn't it? The Pong. In fact, when I was young, the first computer game we had was Pong, and it was only had that one game on it, and it was as big as the house. Now, the thing about this game, Pong, I'm sure you know what I mean. Yeah, is that it was originally played on oscilloscopes, and it was a demonstration. It was some Harvard or someone like that. There was some open day, and one of the professors just hooked up some oscilloscopes to some chips and wrote a bit of code, and it was actually played on an oscilloscope. Which, if you think about it, is just well, the old type of screens anyway, isn't it? But it was played on an oscilloscope. Now, what can you do with oscilloscope? So this is a proper oscilloscope. So again, but the whistling waveforms on the sound card oscilloscope really does operate the same way as this. It just doesn't have the same sort of sample rate. So there's certain things it doesn't quite do. Now, sorry, just have a quick slurp. Now, so this is a trumpet. So you play a trumpet into an oscilloscope and you get this saw wave. And there's a reason for this, and we'll come into this. And again, it's slightly above and beyond, but I always say to my students, and my son got so fed up with it himself, is Fourier transform, Fourier transform, Fourier transform. You will touch on these at some point when you get to university. I don't care what you study, maths, physics, engineering, you will come across Fourier transform. Go have a look at it now. And a lot of students do, and a lot of students even email me later and say, Dave, thanks for the heads up about Fourier transform. Just done a whole unit on it. But what's interesting here is that in a trumpet, we get this triangular wave. And again, we won't go into this. There's so much information out there. If you've got students studying music and physics at GCSE or A level, there's really good books about this kind of thing that they will be interested in. And the trumpet form makes a standing wave. And basically the harmonics that are present mean, and I'll show you why in a minute, make a saw wave. A clarinet, so if you get students that are prepared to come and play these, but actually with the thing about this is with that sound card oscilloscope, I won't waste too much time with this now, but I must show you something about this. If you go to settings, okay, Andrea had a whole course on Fourier transforms. It always amazed me that Fourier, it was all about heat transfer, wasn't it, where it came from? It was a rough mathematical technique that people used. If you look at this part here, input, I can either have where it says loop back speakers, that's my sound card. I'm going to use that in a minute to show you something. If it's microphone array, I'm just selecting the source here, that's my microphone. Should respond. Oh yeah, got to start it again. That's my microphone. Or what I'm going to do in a minute is show you how I play something from the sound card. So again, you could just get a clip of a clarinet. I'm sure there's clips on the internet of just single tones of clarinets or trumpets. You wouldn't have to find a student. But what's important is with a clarinet, you get a square wave, and that's only odd harmonics. Again, if you know sort of what I'm talking about. But now here's what I'm talking about. Now this really is interesting. This relates back to our formants, because if you have a sinusoidal oscillator, a simple harmonic oscillator, it oscillates at one frequency. And this is really what Fourier transform is all about. And that's the line spectrum of what frequencies are present in this oscillation. And it's singular. Okay, so if you, though, have a triangle wave, to make the triangle wave, and this is, again, I've missed a trick here. I should have had a slide in of just showing you how the Fourier series, oh no, it's coming. I know what's going to happen. Sorry, exactly. You see that these, there's F, there's 2F, there's 3F, there's 4F, and when you sum these together, and you're going to see this in a minute, when you sum this together, you make I keep saying triangle, but it's not a saw. My son said, don't say triangle, Dad. It's saw wave. And the square wave is made from odd harmonics. So it's the fundamental frequency 3 times the fundamental frequency, 5 times the fundamental frequency. Now, this is the thing again. So this is the one I may not have put in the, did I put oscilloscope harmonics? Yeah, that's the one, Graham. Oscilloscope harmonics is the link.
There we go. I think that's it. Harmonics series on the oscilloscope.
Yes, so I'm just looking at what Andrew's saying. That's true, Andrew, and there's so much relevance to this. So watch the link, guys, and then I'll talk you through it. So watch it. Someone come back to me, tell me when you're done. Is anyone still there? Hey, we haven't had too bad a drop-off rate. I see, Jenny, that's true. The Fourier transforms are everywhere. They're just everywhere. And your ear is doing it. That's what's amazing. Your ear is doing a Fourier, well, your ear is capturing the sound, but the, is it called the basal membrane? I meant to look that up. But anyway, the membrane in your ear, the way it processes the sound, your brain is doing a Fourier transform of that information. It's separating out your brain. The membrane separates out the frequencies by resonating at different frequencies in different parts. When you look, there's a really interesting thing. I'm sure I've got this right. I read too many things. The connections that come off that membrane and go to the nerves, sensors that notice the motion. If you do the Hooke's law of those, the tension in them is phenomenal. It's phenomenal to be able to carry those frequencies, and it really relates to that A level, the formula between for the tension and the mass per unit length, on a frequency on a wire. It's really interesting stuff there. Hopefully, all right, you're back. I talked over the whole thing, did I? Now, what's important? So I'm going to, is this going to play? Oh no, that's right. I just took a still out of this. Bear with me 1 minute then, because I've been stupid here. I want to. This is the one that I do want to stop. Let me just get this. So just bear with me 1 minute. So just to be really clear what's going on, and what's really cool is we should be able to play this into the oscilloscope. My son made these as sound files for me actually when I first did this. This is one of the first things I put in this talk, and I used, I'll make available the sound files so you can play these same sound files into your oscilloscope. But we're just playing each of the frequencies, okay? Each one you can see it, and then now we start adding them in. And what's amazing is you start to see it build up. And this is what Fourier is you're building up those individual frequencies. And as you add them, as you add all those multiples of the frequency, of the fundamental frequency, you start each term, it makes more and more like a saw wave. And then the last wave is a real saw wave. And this, again, I won't go back. You get what I mean. That the last one's saw wave. And then we do the odd harmonics. So you just add the odd harmonics. I love this, the way this forms. And again, all you're doing is superposing sine waves. It's fantastic, isn't it? And this is a really good thing for students to see. Again, this would be a really good thing in Joe's I can never say it, GeoGebra Joe. This is a really good thing students can do. The Wolfram, all of these programs, you can add these things together. It's really interesting, just out of interest, to show them how a Taylor series adds. I'm talking A-level students, obviously. Our Taylor series adds to make a sine wave. That's another great thing for them to see. But anyway, harmonics, it's fantastic. Now, what else can you do with oscilloscopes? Let's go back to the. Oh, so that was meant to be. This was meant to be before. I've somehow missed moving this slide. So this is just really going back to what we were saying. Well, there's nothing really more to say about this. Just vocal folds, vibrating and standing waves. I suppose what's interesting is we should just quickly say, well, while we have an oscilloscope in front of us, is not only can you do the vowels, the A, E, but you can do the things like consonants like t. I won't try freezing it, but t. And what's happening there is that's actual vortices on your lips. You're making all these little vortices, so there's no real tone as much. Be interesting to see what it looks like in the frequency spectrum. T, t, t. Do you see how there's multiple frequencies there? It's all over the place, and that's coming from vortices. Again, there's far too many different tangents we can go off here. So let's go back to now. So the next thing to talk about is tuning forks. Fantastic things. Sorry, what is the name of the application and where to get it? Is that the oscilloscope I keep showing, Shimmer? It's really important to show you this because, in fact, let's put it in the chat. I've got it here, Graham. So it's the whistling waveforms from the IOP. Basically, I remember when they first started walking, this was a response to COVID, one of the, what can we do? Let's get some things out there. And someone at the IOP basically got permission from this person. So what's really important is that the sound card oscilloscope.exe is the thing you load. Okay, so sorry, I was just trying to read chat box. I forgot what's saying now. Yeah, download the sound card. Remember, I'll just pop it in here. Look, if you want to know anything or anything you think you want to follow up, okay, that's my email, and I'll put my Twitter in a bit, but let's keep going. But the other thing is that I much prefer people to join me on Talk Physics and discuss things, because therefore then everyone benefits. If we have a discussion on Talk Physics, everyone can see it. So ultimately, register for Talk Physics if you're not. If you are and you've not used it for a while, come and find me on Talk Physics. I'm always on there, and we can do something. Otherwise, just email. I know people are busy and everything. Just email me. So the student instructions, and what's interesting about this is it's again, this isn't a comment on the resource. It's fantastic, and this is what else do you tell students to do? Look at how sounds change, whistle into it, look at that. But there's so much more this thing does. I couldn't believe how much more this thing does. I mean, students can explore all sorts of sounds from around the house, but with a bit of guidance. Again, I'm determined to develop a further resource for this, because I just can't believe how good it is. And then the other thing was, again, there's just this video. Again, we won't play the video now, but it's a video for instructions. So hopefully that's okay for everyone else. Download that now. It's good.
Comes with its own signal generator as well, doesn't it? Which is
yeah, absolutely. Sorry, Graham, we could spend all night just looking at this.
We could, absolutely, yeah.
The SIG gen, you can, if I remember correctly, I'm going to do. Oh, is this the problem with GoTo? What you guys don't see is this annoying bar that gets in the way when you're. Okay, so channel 1, channel 2. Let's see what we've got on the oscilloscope. I've got to turn channel 1 back on. Let's do an XY graph. But you can make beats and all sorts. That's right. In fact, I won't just keep clicking things in front of you, but as Graham says, it's got a SIG generator. You can make.
You just need a spare day and you can play with it.
Say that again. A spare day.
I said you need a spare day and you can play with it. Yeah.
I really have. I love it. I just haven't stopped with it. And every time I've found something, it's like my poor son. I'm like, Rowan, come and look at this. He does like acoustics. Now, so I want to talk a little bit about tuning forks. How are we doing for time? Because what I should think about really is, definitely, is what are the important things for you really? Because we've got a good 40 minutes, I suppose. What, I've got to talk for that long? As long as it's beneficial to you guys, that's good. Now, so a tuning fork, where did it come from? They used to, one of the interesting things, again, I don't think we have time to go into, but one of the things I've explored that's interesting for music students is the idea of relative pitch and how everything's relative. If you tune up, you're in an orchestra. Yeah, no, Firefox is a better app, Kevin. That's right. Firefox has a really good oscilloscope. It has a really good frequency spectrum analyzer. It definitely is very good. I think the thing I like about the whistling waveforms is it's so easy for students to just, Key Stage 3 students to just access and get into it straight away. But Firefox is good. It's very good. And if you've been to any Mark Wally's sessions, he's been doing a lot with Firefox and guitars and acoustics. So tuning forks. Why do we need a tuning fork? Tuning forks basically was developed by a trumpeter to tune the orchestra, because you need a standard relative pitch, and there are differences actually in pitches. There wasn't standard pitches over Europe, and some variations in where A was mean that sopranos really suffer in some countries. So one above soprano, desiccant or something, I can't remember now. But the people above, the highest singing range can actually be really pushed by this, where the standard of pitch is, what do we call, they normally use A, 440 hertz is the sort of standard one now. But the problem with a pitch pipe, as they used to tune it with a little pipe, is that it's dependent on, and this goes back to the very first question, it's dependent on air temperature and humidity and moisture and all of these things that affect the characteristic of the frequency and the sound. Is that what they call it? Okay. And so this person invented the tuning fork, and you could do so much with tuning forks. Again, I've not got, unfortunately, you're going to have to listen to me talk about these, but hopefully you get what I'm saying. A tuning fork can be used to actually find a broken bone. The way they use a tuning fork, they can tap it and they move it up and down the arm, and they do this in countries where there aren't x-rays, and the bone will vibrate, or the nerves will vibrate, and you'll feel pain. So they can use tuning forks, but they can use tuning forks in hearing tests. And again, I suppose if I could, you don't need to see, normally if I was doing this in the, in front of you, I'd show you things by putting a tuning fork on my head and stuff, but you get what I'm saying. A tuning fork is used in auditory tests, because if I tap a tuning fork by your ear and you don't hear it, but I tap a tuning fork and place it on your head and you do hear it, then we know the obstruction is, or the damage is pre the vibratory apparatus, the nerve kind of thing that's vibrating and turning the sound into an electrical signal. But if you can't still hear it, then you know that it's the auditory nerve. So they're used in tests. Really interesting. And now this, you wouldn't believe this. I couldn't believe this. This is again Steve Moulds. Go follow Steve Mould. You won't regret it. Steve Mould's video. He used to. I think he tours with a thing called Spoken Nerd, actually, with the stand-up maths guy. If you know what I mean? They do some kind of show. Anyway, this is a tuning fork. This is a tuning fork I've taken out of a watch. I bought 50. And again, you can imagine how small. I used to like taking things apart when I was a kid, and I was always taking watches apart, and there was always this silver little cylinder in there. Never thought much of it, but I took the silver cylinder apart this time, following Steve Mould's great instruction. Again, if Graham wants to find that link, Steve Mould Quartz on YouTube, and put it for you to watch later. Don't watch it now because it take too long. But yeah, I really feel like you should watch that immediately after I finish talking about it, after I finish talking in general.
I'll put the link of his channel up. I'll see if I can find the quartz.
Yeah, you just put, there's so much on there. It's so fantastic.
There is.
If you put quartz, just quartz, Steve Mould Quartz or something, quartz tuning fork. Now get this, okay, now get how amazing this is. And I won't tell you too much because you're going to go watch his thing later. But what we need to watch now, Graham, is the quartz, Milky Quartz YouTube.
Coming up.
And thank you.
And
thanks for doing this.
There you go. There's your Milky Quartz.
Right, so guys, again, watch that. Tell me when you're done. I shall have a bit of my tea. Very cold tea by now. I did tell my son to come and bring me some and leave them behind the door. I bet there's 10 out there already. Sorry, Kevin, it's late in the day. It took me a while to work out what you're saying, but true, yeah, that's right. Yeah, you caused pain in your diagnosis. That Furno's gone quiet. He's gone off, hasn't he? He's gone home. Now, the you are still playing us all out on your saxophone later, aren't you? You promised me. You promised me. I don't know whether you saw Phil's on Visualizing Sound, but what's amazing is Phil's tune. I'm only joking, you Phil. Is the Rubens tube? Phil wrote a tune that had the the resonant notes for his tube. It's fantastic, really good. Now the thing about that, Kevin, is that that's just 2 pieces of quartz. Now the thing, when I lived in Wales, that stuff was everywhere. I used to always, give it to people. I built a rockery from my mum for it. The sad thing is that over the years where I don't live in Wales anymore, I go to visit my mum and I always take 2 pieces of quartz out of a rockery with me to find a good home for. But it's milky quartz. It's just simply milky quartz. It's everywhere. I'm sure it's in Cornwall, Scotland, and Wales. And you get small pieces, big pieces. And now this is what's important. What's going on in that video is, again, I won't waste time getting it up. I'll just explain to you, is that when those stones are being rubbed past each other, it looks a bit like it's sparking, but it's not. It's inside the rock. If you were to do it late at night in the dark, excuse me, those rocks glow. They glow, and it's called the piezoelectric effect, or triboluminescence, but it's to do with the piezoelectric effect. And the idea is, if I squeeze a piece of quartz, I produce electricity. I could also put electricity into a piece of quartz and make it change its shape, make it oscillate, if I use oscillatory current. Now here's the bit. I'll just say one more thing about the milky quartz, because this always amazes me. There was a Native American Indian tribe. I can't remember their name, the Hopi something or something Indians, but they basically used to put bits of milky quartz in their rattles for ceremonies. And was it the Hopi Nation? That's what you meant to say now, isn't it? That's right, the nation. That's right. I read a very interesting book once called 7 Arrows about all the different nations, but the Hopi Nation, that's right. Thanks, Helen. And they basically put milky quartz in rattles with very, very thin leather skin, shook these things, and they glowed in the dark. So, but now let's see what we do in terms of this quartz now. So what I want to explain, so this is a piece of quartz that's been cut. This I took out of a watch. When you watch Steve Mould do this, he's got he connects an oscilloscope to the wires and flicks it, and you see the signal it makes. But what I want to get across to you is that this is a real tuning fork. Some watches run on mechanical tuning forks as well, but this is a tuning fork. When it's squeezed, remember, if you squeeze the quartz, it makes a current. So when this thing oscillates the quartz, it makes a PDF that's changing. Okay, now now remember we said to what drove the electronics industry was amplification. And this is why you need amplification. So this thing's oscillating, it makes a signal. The signal is fed to an amplifier and is fed back to something that oscillates it. So it's like a positive feedback loop. So the thing's oscillating, it's making a current, and as long as I can supply, excuse me, sorry, as long as I empty an energy store somewhere else, then I'm going to basically be able to put that energy into this system and keep this thing going. So that's why your quartz watch has a battery. It's got nothing to do with keeping time, as well, in the sense that it keeps this feedback loop going. Now, I don't want to say too much because it's all in that Steve Mould video, but I'm going to say one thing just because it really fascinated me. And these things have been made to oscillate just outside human hearing, because no one wants a watch that makes a noise. But if you put one of these close, a quartz watch close enough to a dog, it will hear it. Yeah, actually hears it. Now, the other thing you can do, so I was amazed. I bought 50 of these for about, a couple of quid, 50 of them, but they're in a silver container. You've got to watch just in case you want to do this. I did sort of message Steve and ask him, and he kindly told me how. It is apparent in the video really, but what you're doing is you're putting a plier. If you watch the video, what he does, and you want to get one out, he's not cutting the top, he's using pliers, and you'll see what I mean when you watch the video, to squeeze the top in lots of places to break the actual glue, and then it just pulls out. But I'd done about 15 out of me 50 before I messaged him and asked, and I was just trying to cut it out. But now I've got about 10 of these ready to play with. So that, get one out, attach it to an oscilloscope, look at the vibration. Now, what else can you do with tuning forks? This is a program called Audacity, and you could probably do something similar to this with the oscilloscope that we have. But what Audacity has is, this is its frequency spectrum analyzer. And what I like about this frequency spectrum analyzer from Audacity, which is free, is that you have the frequency on the y-axis, shall we say. The x-axis is time, and the color, the brightness here, is intensity of that frequency. So there's 3 bits of information on this graph. All right, so Jenny says she can hear them. Well, it's only just outside the human range. I mean, do you hear bats? Now, yeah, excellent. Audacity is so good. There's so many things you can do with Audacity. Now, when I tap the tuning fork, so I tap the tuning fork, and you get this sort of big boom. That's the sort of bulk motion of the material. This ting's an interesting thing, because this ting here, that's kind of the metallic. That's also sort of bulk movement of the metallic. And if the cheaper the tuning fork, the more prevalent that sound is. Never get those 2 words right. So basically this part here is kind of we're not really interested in that. What we're interested in is, so you've got different harmonics here, but the thing about tuning forks, they make a very pure frequency in the actual. I've got a 50 hertz tuning fork. I don't know whether I put the slide into this. I can't remember now, but again, in the write-up, I'll explain about it. And it was used for setting standards of frequency before we had electronic means. So they dive very quickly, and the red here, that's the tuning fork, that's the tone, that's the frequency of this tuning fork that we're hearing. Now, this 50 hertz hum, okay, it took me ages to work out what that is, but that's an artifact of the computer. That's inside the transformers, flashing backwards and forwards, making a magnetic field that's alternating, that's also is superimposing on top of the electrons in the wires its own 50 hertz hum. It's quite hard to get rid of that, but in really expensive stereos, they use a thing called mu metal. I think it's called mu metal, which is an alloy that basically confines magnetic fields. It sort of, I have to really think about it to talk about it. But it basically reduces the magnet. You put it over transformers, let's just say it like that. You put mu metal over transformers and it stops them affecting the circuits. So that it's interesting, that 50 hertz hum, that is literally the transformer oscillating, and then that's creating a magnetic field, and that magnetic field is sloshing the electrons backwards and forwards in the wires as well, and it's superimposed. Now, okay, guys, I don't know whether I put this in as a link for Graham. Yes, now I've got a warning here. Don't put the link in yet, Graham. No. I've got a telegram. Don't like spiders. Don't watch this bit. We'll tell you when it's stopped. This, if you're spider phobic, I feel it's my imperative to tell you not to watch this. Bit like Trevor's vocal folds. Needed a warning. So Graham will put in the spider. I just want to show you something interesting, and you guys watch the clip, but don't watch it if you're spider phobic.
Big spider.
Got a mic on. I feel like a naughty student looking at my phone under the table.
Dave the Spider Charmer.
So has everyone seen that now? Have we? I won't. I've got to be careful.
I think so.
Yeah. So now, what's interesting about this is I heard the tuning fork oscillating, and I thought that sounds like about the sort of rate of a blue bottle. It sounds like a fly. I thought, I wonder. And apparently I've found out that people that study spiders, they entice them out of webs like this. So it worked. And what's really interesting about that, because it takes a while, it's very wary, but once it focuses on that, you can see I'm pulling my hand away, worried it's going to run up the tuning fork. But what's really, well, the more I looked into this, and again, I should really have a graphic for this, but spiders tune the tension, although not all of them, not all different spiders use webs in different ways, but some spiders, I think like the golden orb would do this or something, they tune the web, let me start again. They change the tension on different threads that are radially outward so that they can get directional information from the frequency. Isn't that clever? I knew they were clever, those spiders. So they're not, they're not just feeling vibration. They get directional information because one region of their web will vibrate with a different frequency. Because although the fly is driving it with its oscillation, the tension will affect the resonant frequencies that come down. So it's incredible, isn't it? Spiders do that. And there's so much. I can't even remember the things. I read so much more about that. I've started the video, haven't I? I don't want to do that. Cool. So I'm just getting. Now I'm not going to go into this one today. I decided not to go into this one today. It's normally something I set up, and it's basically I show you about if you oscillate a ferromagnetic material in a coil with a magnet, you can make a tone. And it's a shame. There's just too many things to talk about, and I've got much more interested in the voice recently. So I wanted to go down that route, but I usually, this was my pièce de résistance on the original talk as I kind of made it. So I will write this up on Talk Physics. I'll make sure you get to hear about it, because what's incredible about this is that they made this for Morse, this technology for Morse, and what we're trying to say, to generate that continuous tone. So this was like that thing I was saying at the beginning, that amplification and the ability to drive a continuous tone. So this was to just drive a continuous tone, a carrier wave, carrier signal, to put the much weaker signal, piggyback it on. But Hammond, Hammond organ basically took this technology, and what happens in a Hammond organ is you have a ferromagnetic wheel rotating in a magnetic field. It's all, I'm such a fool, I should have set this up because it's such a good bit of physics. And it basically makes a signal, and Hammond organs put different tone wheels in engage them to make the different frequencies. But again, sorry, we'll just have to do that one another day. What's going on with my PowerPoint now? So the next thing I wanted to talk about was beats, because there's about two things I really want to get in before, because time's running out, isn't it? So beats. So let me just check what links I sent, Graham. I think I said, yeah, the first one.
Beat SIG-Gen, yeah.
Yeah, I only put one of them actually, but yeah, beats.
You did.
Yeah. I can't remember which one. Hopefully it's the SIG-Gen one. In fact,
It is. It is.
Yeah, that's
it's called Beat SIG-Gen. Yeah.
Yeah, that's the one I want you guys to watch. So again, watch the vid. Come back to me when you're done. It really, Andrew, you wouldn't believe the amount of books I bought in lockdown on sound, just sound and building acoustics and things. It's unbelievable. In fact, I should shut up when you watch the video. Is it longer than I think, that video?
I've just finished it. It's just over a minute.
Oh, yeah. So the thing I'm getting across there is that, I mean, admittedly, I have 2 SIG gens, and you don't always have that. So we'll talk about that in a second. But beats are something that really should be shown to students. They are the example of supposition. The problem is we only deal with the extremes when the two anti-nose line up or nose line up. That you get the idea. I mean, but we only really talk about those extremes. But I always show my A-level students how beats are formed, the sort of the supposition. But what you don't, for GCSE and Key Stage 3, you can just show students supposition and how waves interference. And what as you saw in the video, you're sort of turning one SIG gen on and then turning one SIG gen on, so that they can hear there are 2 separate tones, and then you put the 2 on and you hear the oscillation, the change in amplitude. And what's interesting about this is that I've not made it yet because of lockdown, but we basically were going to do a physics of music day at over here, Graham, Chetham's. I can never say it, but the music school.
Chetham's in Manchester.
They call themselves Chets, but it's Chetham's, don't they?
Yes. Yeah.
Yeah. And we planned, and I think some of you came to it. We did a prelude to this online. It's one of the sort of IOP's kind of responses first. We thought we were about to do this day, and we just thought, well, let's still do it online. However, we're still going to do it for real, and I've got some demos being made for me, and one of them is to do with beats. And what it is that I was amazed by this. You could always, and I laughed to myself, and I thought you could always find an application. You show me a phenomenon, a physics phenomenon, and I'll find an application of it. And with beats, what they used to do, and I haven't found much reference to this. That's one of those things that just doesn't come up. But they used to get 2 organ pipes of the same pitch, have one being played from air on the surface and one being played from air that was from the mine. Okay, so it's coming up from the mine, and if the air from the mine comes up and it's denser because it's got pollutants and toxins in there, sulfur dioxides and things, then you'll get a change in frequency, if you get what I mean, from the change in density. And therefore you'll hear that change in frequency will be quite slight enough to make a beat. So someone used to sit at the top outside of the mine listening to 2 organ pipes playing, and if you started to hear some warbling oscillation, then they'd say, clear the mine. There's a denser gas coming up from inside the mine. It's incredible, isn't it? And this person, it's called Sam Underwood. I follow him on Twitter, and he was always making crazy. He makes crazy things like infrasound machines for the BBC that shake things and stuff. But what he's making me is a little demo. I saw he'd made these tiny little organ pipes and was playing them. And he's the sort of person that just knocks all this stuff up from wood and things like that. I said, could you do this for me? Could you do this for me? And luckily he's as excited about sound as I am. And he's going to build me 2 little organ pipes. And one you can actually change that you can play it with carbon dioxide instead of air. Might have to play with the mixes, actually. I'm not sure. I've not thought this through yet in terms of getting the frequencies only slightly different enough to make a really nice beat. But the idea is that we're going to have a denser air going through one, and we could tell this story and show it as a phenomenon. Sorry, you can tell I get excited by beats. Now, the other way, say that again.
Can't wait for that. That sounds really good. Looking forward to that.
Yeah, no, I probably keep thinking of things I want him to make me. He's making sort of sirens at the moment. There's so much interesting. Sam Underwood is on Twitter. He's just worth following just to see the crazy stuff he builds. Now, what I'm going to do next is just quickly show you about, again, I don't want to play these. There's no point in playing these, but you can make beats with tuning forks and Bluetooth to make one of them slightly more, the mass different at the end here to change the frequency. But there's tiny little neodymium magnets. I've found now, I just keep one of them on one tune, or a few of them on one tuning fork. You keep them by the handle. They don't affect the oscillation, so you can just show that the 2 tuning forks together have the same frequency. Slide one of the magnets up, changes the frequency enough to get a beat. So it's a really good way. Like I say, I used to use Bluetooth, but now I just have a magnet permanently stuck on my tuning fork. And the other thing here I'm showing, and Mark Wally did this really well. He had 3 phones. I don't know if anyone know, it was in one of his sessions about a week and a half ago. He had 3 phones, one with Firefox on, okay, and then the other 2 were doing the beat. So you can, it's one of those rare lessons, get your phones out, get your phones out. You what? Get your phones out. And you know, pair off, and you get sig gens. There's loads of free sig gens you can get to download, put on your phone, and you detune one, and you know, you can hear the beats. It's fantastic. Oh, oh no, I didn't see that. And the other thing about the beats is it's often a way to tune. You know, when my dad reminded me when I played in Frodge and Silver Band when I was a wee lad, that we used to tune the trumpets using beats. Now, just a couple of quick things. I wouldn't be me unless I talked about Salford acoustics. This is interesting. I found this really interesting. This is a book on light. And we don't see this phenomenon very much anymore. But in the olden days, when like horse-drawn carriages with their spoked wheels used to go past each other, people have described in the past seeing weird phenomenon, and they're seeing optical beats. And the thing about this, and sometimes you can come out of the stations that, again, they cut down all the metal fences, didn't they? But pre that, as you came out of a station and moved past sets of railings, you can get some weird beats. I just like putting that slide in because there's optical beats. Now, this is what we want. So just let me, I should have had these up already. So Salford Acoustics, this is the website you want. Okay, let's just pop this in to the chat. I'm putting the careers page in, but there's all sorts of pages here. There's things for lesson starters. So there's some really interesting information here about careers. Again, I don't need to take you through it. You can go look at it, but I'd really save that link for your students, talk to them about careers and acoustics. But the thing I really want to talk to you about is these different lesson starters, and one of them is a thing, the confuser phone. Okay, so again, I'll just go back to my PowerPoint now for now. So not that I don't like talking to you guys, but I've got such a big chili I made myself earlier. Anyway, physics. So this is Salford Acoustics. We interact with them a lot. They let us take students there. This is the anechoic chamber. There's all sorts of things. But my son, I like telling my students this, and that I think this is one of the reasons they go and study at Salford, is that you actually get to, once a month, they open this up to the students to jam in. And they have hard rooms, hard reverberation rooms. And my son was saying his flute sounded like it played chords in there because of the sustain. And apparently, for some reason, I've not quite got into this yet, but the bass sounds very good in the anechoic chamber. But look at this. I'm just hoping I've put the right, yeah, it's okay. I've put the slides in. Just quickly talk about this. So this is called the confuser phone. And it's fantastic because you might have seen these in your career before. You know, the student closes their eyes, you click on this side and then they point the other way. But what's interesting about this is you've got, it's all about the distance between the ears. Speed is distance over time. So there's some good stuff there about how we tell direction. Now, some things, it's too small. So an insect, the reason why they have their ears, why they hear with their legs, is they can get their legs far enough apart to get a measurable time distance for it to be meaningful or processable, I guess is the word. However, you must make a confuser phone, and they are fantastic. They really are, and it's all on that website. Hopefully, the link, you know, is in the thing. Copy these things out. I think this chat, I should know this. The chat gets saved, I'm pretty sure, on your hard drive.
Should be doing, yeah. Should be in the documents.
I'm
Yeah.
sure it does that, doesn't it, Graham? Yeah.
Should do.
This really, geckos have what's the word? Geckos have a hole through their head. They don't have the same apparatus as because they can't get directional information. Their heads are too small. The distance that the sound wave would travel is too small for their brain to process. So, it doesn't, if you're on the web version, does it? I don't know. Okay. I mean, it will get put on Talk Physics. And if you have any problems, of course, remember, I put my email in the chat. People can just email me and, you know, we can get things to you. where was I? So yeah, this is really good. This is really cool. I learned this. Guess who I learned this from? Guess who I learned this from? Whose video channel was I watching? All together now, Steve Mould. And Steve Mould had this brilliant little clip about asymmetry. So we, think about this thing. We're getting directional information in this plane. Owls have vertically asymmetric ears. I've not got a picture in my PowerPoint, unfortunately. I've got one somewhere. But owls are virtually asymmetrical ears, and that's so they can get directional information in the up and down. And it's incredible, isn't it? Now, where did I go with this? Let me just see, because we're running out of time. We don't really want to watch this. So again, I wouldn't be me unless I told you about some amazing books. And this is Trevor's book, really good. We've got 4 of these in the library at college, and they're always out. Students love it. And this is this interesting thing about when you clap by stairwells. I mean, Pink Floyd used to they used to record the drums in a stairwell, a famous stairwell for the acoustics. And you can get some really interesting sounds out of stairwells because of the reflected waves. And the sad thing is you can't take an acoustician anywhere without them clapping. So I come out of a friend's house about 3 in the morning with my son, and we were going to get in the car, and we're in between 2 houses, and he starts clapping, going, "Oh, listen to the comb filtering here, Dad." And it's like, come on now, you can't do that. Sorry, what's Kevin saying? I see. Oh, I'm just copying it all. Yeah, before we close it down. That's good.
I'll make sure it all goes up on Talk Physics. So the 2 of us can make sure that happens, can't we, Dave? Yeah.
Yeah, definitely. I definitely get it onto Talk Physics. So we're just running out of time. So let me just jump to a couple of things that I think are important. I want to leave the PowerPoint. Why won't it let me out? Oh, sorry, it's got to the slide. Ooh, I've gone past it now. Oh no, I have closed the PowerPoint. So what have I been reading? That's not one. So again, these are really good books. This is the one I found out the thing about the the ripple tank being used for waves. This is the book. It's probably even worth taking a picture of the screen. I'll leave it up for a second because this is the Charles Taylor book that goes with the Christmas lectures. And to be honest with you, when I first thought about making this talk and I went and put my pitch to the Anthony Waterhouse, like I hope some of you do, this book, I found this book and it was like my talk in a can. Fantastic. I mean, obviously I've made my own directions, gone different ways, but there's 5 lectures and this book's fantastic. Again, this was a good one for students about music. The Sir James Jeans book, has everyone got a picture that wants it? Again, I'll put these things on Twitter as well. Is what's interesting with this, if I just go to the next slide, is the James Jeans book, everything apart from this one and this one, was it some or the more modern ones actually, the James Jeans book, but these were all books it referenced. And I've never done that before. At the beginning of the book, it had a dedication. So the James Jeans book said, I'm indebted to these authors for their titles, made a list. And I went on Amazon that afternoon and bought them all. And they were all only like £5, £3, £2, I think there's a couple like this new one here was £15, but most of these were £3 or £4. And I've never done that before. I just went into the front of that book and bought all the books that it referenced. Lissadue figures that we could go down that route. How are we doing? We've only got about 7 minutes. Is there anything, you guys? Let me just show you 2 more things because my son made these and he'll be gutted if I don't use them. He's training to be a teacher next year. So this is beats. Again, I'll put this out. This is just, I want to close that show, don't I? That's where we go. Hang on. Just give it a minute. I don't know why that seems to be only on. Anyway, the point about this is that this is my son's little guide. So it's about Audacity, how to make beats in Audacity. You can do this in anything that produces 2 independent streams. But what's interesting about this, again, I'm just flicking through this thing, but what's really interesting is you take these 2 waves and then you make another, again, it's all instructional there, and you get another, you get the supposition of these waves. But what's really cool about this, if you think about this has gone nowhere near a speaker. This signal is internal to the computer. This signal is internal to the computer, We combine them, and this is what you get. And my son was really thinking deeply about this and going on about how it's even more weirder than that, because the digital representation of this is being mixed with the digital representation of this, and getting a digital representation of what we would hear and see. Sorry. Go play with beats. They're fun. But it's interesting to know whether the beat is in the air, like with those SIG gens, or whether the beat is an artifact or it's within the equipment. And then I've still got a few more minutes because, like I say, my son made this, and it's quite interesting. We won't go into it in too much detail, but this is something I'll put on Talk Physics, and you can share with any musical students. So in musics, we're interested in defining a sort of a range. We divide a doubling in frequency into 12ths to make an octave. What's really interesting is these tuning systems. Again, it's to do with these ratios. I won't spend too much time on this now, but go and look at it, or get your students to look at it. They're into music. And Pythagoras, it's called just intonation. Again, I'm not going to mess around playing these things now, but this PowerPoint you could download and have a play with. Give it to music students. Now, these are the ratios that make the sounds. Okay, so we're saying the D, and it's this ratio from the original C. But just intonation has a problem. What happens is that if I take a C and move to a G, okay, and then I take and look at the ratios, the maths of that ratio, and then I do an E flat to a B flat, which is the same number of semitones, okay, but it's a different pitch difference, ever so slightly. It's called the Pythagorean comma. And when you sort of transpose music, the thing about these little ditties, these trumpet ditties, again, you download it and play them. My son's written, a little ditty in the key of C and a little ditty in the key of E flat, and you'll hear the difference. They don't transpose, in just intonation. So the solution to that, okay, let me have a look. I think I went too many. Problem with just intonation. There's a bit of a delay now, isn't there? Here we go. So that was the problem. I keep missing the slide I want. So the solution to this was a thing called, here we go. A thing called equal temperament. This is where my students call me a boomer. It's got equal temperament. Okay, so what's happening now is we have a ratio here. The ratio we're using is not these nice little ratios. And what's really interesting about this is we're going from a rational to an irrational number, because it's all to do with it's all to do with the sort of the basic unit is a square root of 12. And it's interesting why 12 comes into so much to numbers, because it's so divisible. I mean, a load of old number systems used to be based on 12. I'm going off on a tangent there. So again, it's all relative to the standard of pitch, and that's interesting. Then last thing, I'll be so pleased that I've got this in. So if you've got a groan tube, I don't know if they're called different things in different parts of the world, but the tubes that you turn up and down, upside down, and turn the other way, and they make that sound. I've got a picture one coming in a minute. This is a thing, it does a weird thing called comb filtering. Again, you can play these. My son made this, so I was really pleased with this. So I really like people to use it. This is the ground tube. Okay, so this is the last thing I'm going to say, and then I'll shut up. And then, what are you going to do? The survey? Graham can pop that in now if you wish. These are the ground tubes. Okay, so what happens is this little thing here, it slides down the tube. This is what's really amazing about these. It slides down the tube, and it slides at a pretty much constant speed, so it produces the same tone effectively, but you get the weird sounds. Okay, you get these different weird sounds. I don't think it's going to play it. I won't try playing it. There we go. Yes, but these sounds. Now, this is what's weird. This is the thing. This is all I say, and then you can go download it and play with it and see what it's really saying. As that thing moves down, the distance between the bottom and the moving thing, this changes what what frequency is resonant from the heart. So you still have the fundamental, which is the thing moving down, but different frequencies get promoted as being, they get more amplitude, more energy, different frequencies. And that's what makes that weird sound. I mean, it has no real application as such. It's just a nice sound. But there are that kind of filtering is used in other sort of things. I won't go into those now. Just to say that what we're after in architecture and building concert halls is we don't want places where we get standing waves and we get nodes and sounds cancel out, or where things become louder. And it's amazing how much design goes into concert halls and auditoriums, and even festivals. The teams of people go out and test out all these hotspots. And in fact, there was one of the projects that my son was offered as an undergraduate was to write a computer program that would looking at this, which would tell the mixing desk, because the mixing desk sits in the middle, it's got equal path length from both speakers, it's all going on, isn't it? But elsewhere, you get regions where frequencies cancel out. And the last story I'll tell you is that there was the salvation. It's amazing what you can do with frequencies and filtering, and this is why Fourier transforms are so important, because Fourier transforms you can filter things out of the Fourier transform. And there was a Salvation Army band, and they were playing a Christmas concert, and there was someone with Tourette's in the audience, and they kept saying whatever it was they said. And when asked if they asked the conductor if they wanted the person removed, and he said, no, of course not, you can't do that. But don't worry, we've got really clever software that will be able to take their frequency out, their dominant frequency out. Unfortunately, their dominant frequency was the same as the B flat horn solo, so it couldn't be removed. Okay, well, I've really enjoyed that. I really hope you have got something out of that too. It's been a grueling 3 days, but it's worth it. I'm done now. I finished teaching for the year as well. So thank you.
Thanks, David. You've been a star. You've been an amazing, phenomenal training CPD
this is something I've
extravaganza.
built up for a while. And apply. Sorry for butting in, Graham. Apply.
No, go for it.
It's this gave me what it gives you. What's interesting about the Anthony Waterhouse is you get some money for your time, and what's more important is you get money for equipment.
You got the resources, brilliant. Yeah,
that's right. Yeah. So, guys, before you go, make sure you do that survey.
We keep forgetting to say about the raffle prizes. Well, we need to.
Oh, I always keep forgetting to say that we have some.
I do as well.
And we have some Ben Rogers. What's it called? I'm looking at it.
The 5 big ideas, isn't it? Yeah.
Yeah, we've got some of those to give away for people that complete the surveys. So do the survey. Have you put it in the box, Graham?
I have. Yeah, 1958. It's there. Yeah.
Especially this one. I was just,
absolutely.
Graham's my boss.
I'll send you a contract for next year now, David. It's been a superb 3 days. Thank you very much indeed for
I really have.
together.
I really have. Yeah. I got my family coming round tomorrow for a segregated, because we're all still building really, but we've got different zones in the garden.
Yeah.
And buckets in different sheds.
Yeah, so all the resources, as people are filing out, all the resources are going to be up on Talk Physics, so make sure you go on Talk Physics to the North, Teaching Physics in the Northwest group. It will be there for you. Yeah, I should have. Me too, I should have done as well.
Do I need to save the chat log, Graham, or